Hey, today we're talking about implicit differentiation. This is section 3-8. So let's start by taking a look at this function. It's this equation. It is the equation of a circle. And if I want you to find the derivative, so find dy dx, the problem is that everything that we've done up until now has been solved for y. And what we've been talking about is just techniques for finding the derivative of this part over here. And this equation is not solved for y. So in order to do that using the techniques that we've had in the past, we would have to solve this for y. So we'd subtract over the x squared, and then we'd square root both sides. And when you square root both sides, you throw a plus or minus on here. So you can see that right away this gets very complicated. What seems like a simple function, when you solve it for y, all of a sudden it not only is it a chain rule, but you've got a plus or minus here. So you have to actually create a piecewise function to define it on different values for x, which becomes complicated very quickly. So implicit differentiation is a technique we use when an equation is not solved for y. All right, so let's take a look at how it works. The idea is you leave each term where it is. You don't solve it for y, but you're going to take the derivative of both sides. So derivative of this side, and the derivative of this side. Okay, keeps it all even. Everybody in algebra land is happy. And we learned earlier that the derivative can distribute, so this becomes the derivative of this term, the derivative of this term, and the derivative of the other side. Okay, so let's go through what these are. Now remember, everything's a chain rule. Okay, so let's talk through this. The derivative of x squared, it's the derivative of the outside function evaluated at the inside function times the derivative of the inside function, which in this case is 1. The derivative of x is 1. All right, so now I just made it more complicated, like it's a real simple derivative, but I want you to remember that everything you're doing is a chain rule. It's just that in this situation the inside function becomes a 1 when you take the derivative. But that's important in this next term. So let's take a look at that. The derivative of the outside function is again a power rule. Drop down the 2, lower this guy by 1, evaluate it at the inside function, times the derivative of the inside function. Now, what is the derivative of y? Well, it's just dy dx, right? That's been our notation all along. That's the derivative of y. So what this side, I'll come back and do the right-hand side of the equation. What this becomes is 2x plus 2y dy dx. Okay, and then the other side of the equation, the derivative of 25, well, that's just a number, so it zeroes out, and this is 0. So this is the derivative using implicit differentiation. Basically, it boils down to this. Because of the chain rule, anytime you take the derivative of a y term, you have to add on dy dx, because that is the derivative of that inside function, which is y. And the advantage of this is, what are we trying to find? Oh, we're trying to find dy dx. Well, look, right, it's right here. Now we just have to do some simple algebra to solve for it. So I subtract over the 2x, and then divide by the 2y. And if we reduce a little bit, I get that the derivative is negative x over y. So much simpler than dealing with this scenario with the square root. So bottom line, if it's not solved for y, don't try to solve it for y. just take the derivative term by term, and every time you take the derivative of a y term, label it with a dy dx because of the chain rule. Okay, let's take a look at another problem. We're going to go okay, and the directions are find dy dx. So we're going to take the derivative term by term because this is addition. Now if this was multiplication, we would be doing the product rule. Okay, so all the same rules apply to the derivatives. It's just that when we take the derivative of this side, it's addition, so that means we're taking the derivative of each term. So if you want to write it out, you can term by term. You don't have to, but here's what it looks like. d dx, tangent y, and then the right hand side Okay, so the derivative of this first term is going to be 20x to the fourth. The derivative of this term, this is the derivative of the outside function of tangent is secant squared. Evaluated at the inside function, which is y, times the derivative of the inside function, which is dy dx. Okay, equals. Now this right here is another chain rule. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, and then your last term. Derivative, technically it's a chain rule also, but because it's an x term, the derivative of the inside function is just 1. Okay, so what you can see now is algebraically we have 2 dy dx's, and we spent a lot of time, if you were in my class at least in pre-calc, we spent a lot of time on dealing with algebraically how do we solve for something that we have 2 of. And your plan is to get them both on the same side and factor them out. Whenever you have 2 of something running around, that's your plan. So we're going to take this term and move it over here because it does not have a dy dx, and I'm going to take this term that does have a dy dx and move it over here. So I have secant squared y. I'm going to put this dy dx in front just so we don't get messy. And then I'm going to subtract this term that I'm bringing over, dy dx to y. And then on the right hand side I've got that 5 still, and I'm subtracting over this over the 20x to the fourth. Okay, so just rearranging. If you need to do that in a couple steps, please do that. Once you have your 2 things that you're solving for on one side, you just factor them out in front, and that's how they become 1. What I'm left with in the first term is a secant squared y, and the second term is a 2y. And then you divide by all this stuff. So dy dx is 5 minus 20x to the fourth over secant squared y minus 2y. Now, and that's your derivative. This is pretty amazing because look at your original function. I mean, even if I wanted to solve that for y, I wouldn't know how because I've got this y here and I've got this y here that's bound up in the tangent. I'm going to have some kind of inverse tangent of a bunch of stuff, and I don't even know if it's possible to get y by itself there. So this is a huge, powerful tool. So pause the video and try to do example 3.69. It's very similar to this one, and then I will do one more problem for you when you get back. Okay. Tried that problem. Hopefully that went okay. We haven't done a tangent line problem for a while, so find the equation of the tangent line of this function at this point. 3/2, 3/2. Okay, so we remember the plan for the equation of a tangent line. First, you need to find the derivative. Next, you plug in your x point to find your slope, and then find the equation. So first, derivative. Since I've got mixed x's and y's, I'm going to do implicit differentiation. So I'm going to take the derivative of each term. Okay, derivative of 0 is 0 on the right-hand side, so I guess maybe I should just write that. For formality's sake, we are taking the derivative of the right as well. Derivative of y cubed, chain rule. Derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, next term, also a chain rule. Derivative of the outside function evaluated at the inside function times the derivative of the inside function, which is 1. Minus, now look at what we have right here. This is actually a product. So this 3, we'll just bring the 3 along for the ride with the x and the y, and those are my two terms. So the derivative of this guy is going to be subtracted. I'm going to put brackets because the whole thing's subtracted. The derivative of the first term times the derivative of the second term plus the derivative of the second term times the first term. That's my product rule, and that equals the derivative of 0, which is 0. So let's take a look at these two derivatives. I'm going to recopy everything else. Okay, now derivative of 3x is just 3. And the derivative of y is dy dx. Okay, my subtraction sign can distribute through. And I've got 2 of these guys that I'm solving for. So I'm going to move these non-dy dx's over so that I group my dy dx's. So I get a positive 3y and a negative 3x squared. And then I factor out a dy dx. Okay, and that's my derivative. Now, the next step is to plug in your x value. And normally when an equation is solved for y, all you plug in is the x value because that's all you have is x values. But when you use implicit differentiation, you've got x's and y's. So what we're going to do is we're going to take this derivative and we're going to plug in both the x and the y. Okay, so this looks like 3/2, 3/3 squared, 3/3 squared, and 3/2. Okay, now if you do all that out, it's a big mess on your calculator. You get -1. Okay, so that's going to be your slope of your line. I'd like to note that you can plug this point in any time you want after you take the derivative. So here was, where did we end? This was our final derivative before we started solving for dy dx. You can plug in the 3/2 here, and that actually makes the algebra easier. I didn't do that because I wanted to show you and give you more practice with this algebra that you will have to do on some problems. But the sooner you can plug that number in, the faster it is to get to your slope. And you still solve it for dy dx, but you don't have to do all this manipulation. Okay, so you could go back and you could try this problem plugging in this point here and make sure that you get the same answer. And now my last step to find the equation of the tangent line is just to plug in either to my point slope form or my slope intercept form. It doesn't matter. Whoops. Yes, and that's my equation of the line. Look a little bit different if your slope intercept form, but it's all good. Either way is fine with me. That's the equation of your tangent line. Okay, that's all for this section. I'll see you